Hi everyone, this is Bert de Vries and this is the Bayesian Machine Learning and Information Processing class. Today we're going to be talking about latent variable models, models with hidden variables, unobserved variables, and variational Bayes as a means to approximate Bayes rule, to do approximate inference. So quite a mouthful, so let's get started. So here's a data set. This is a data set from Old Faithful, which is a geyser in Yellowstone Park in the USA. It's a two-dimensional data set. I have x1 and x2. And well, there are two classes. You can just see that, right? Given this class, it would be reasonable to make an assumption that the data has a Gaussian distribution. And given this class here, it's also reasonable to assume that that data has a Gaussian distribution. But the class labels are not given. So let's say that the task is to build just a model for this data set, so P of x. We are not interested in building a classifier. We're not interested in building some discrimination boundary here, just a model for this data set. I can't assume a Gaussian distribution. I must assume something like two Gaussian distributions, given the class, it seems like I have a Gaussian distribution. So we have had this problem before in the generative classification class. So let's build the same model here, just we don't have the class label given. Now, when we talk about unsupervised classification, it's called clustering. So rather than a class, we speak about a cluster. So let's go build that model. I have observations d, x1 through xn. So it's not x1 comma y1, where y1 is the class label. It's just x1. The class label is there, but it's not observed. So we're going to build that model just like we did for generative classification. We're going to assume a class label, z of n of k. In generative classification class, I wrote here y of n of k. It's the same variable. I just write here a z to indicate that it's not observed. So z of n of k equals 1 if the observation belongs to the kth class and 0 otherwise, one hot coding. And given that my observation is from the kth class, the data is distributed in a Gaussian way with mean mu k and sigma k, or variance sigma k. So in this graph, that means there's a mean here and a sigma about this wide, and there is a mean for the second class here and a sigma about this wide. So that model is a good model. We're happy with that. I can write this out all the way as a generative model, a probability distribution over observations and class labels or cluster labels. And this model looks exactly the same as we had in our generative classification class. The only difference being that there we talked about y of n of k, and which was either 1 or 0 and was observed, and here z of n of k is also either 1 or 0, but it's not observed. This is called, when z of n of k is not observed, it's called a Gaussian mixture model. And the reason is that if we integrate the hidden variable away, the latent variable z of n, and we can do that here just by marginalization. We take the joint and we integrate, or we sum over all possible values for z of n. We get this model, and this model basically is a weighted sum of Gaussians. So it's sort of a mixture of Gaussians. So that's why it's called a Gaussian mixture model. This model is the same as this model. Here it's been written as a joint over all variables in the system, x of n, and unobserved variable z of n, and here just as a marginal over the observed variables. Now, there is a difference between the parameters mu k and pi k and z of n of k. both of them are unobserved in a way. They are both latent variables. But mu k is not a function of the observation n, right? It's a parameter for the whole system. Z of nk is also a latent variable, also unobserved, but I have a new variable for each observation x of n. So sometimes we call these variables z of n states, and the variables that do not change over the data, we call them parameters. But from a Bayesian perspective, they're both just latent variables, and sometimes we use the word unobserved variables, hidden variables. They all mean the same thing. So this is our model, and good. So I can work that out into a log likelihood or in a likelihood function. I can come up with priors for the parameters mu and sigma and try to do Bayes' rule, and it turns out we can't really work with that. It's analytically not solvable. We cannot come up with priors that for the given basically for the likelihood function, and the likelihood function we mean by this, basically the probability for all the data given all the latent variables, the parameters, but also the class labels. Now we cannot come up with a good prior for this, that if I multiply it will give an analytically computable posterior. So that's a serious problem. Yeah, so how do we deal with that? Well, we're going to talk now about a variational Bayes. There's basically two ways to deal with this. One way is Monte Carlo sampling. The other way is variational inference. Just because we have a limited time in this class, I have to make a choice. I think variational inference is more interesting, so that's what we're going to do in this class. For a moment now, forget about this particular model. What I'm going to talk about applies to all latent variable models, all models that have observed variables and hidden variables. And we make some observations, and we want to go from prior distribution for the hidden variables to a posterior distribution. And we used to do Bayes' rule. We're going to do a different kind of concept here. We're going to derive. First, I'm going to write new information in the form of constraints on the posterior. What I mean by that is a data constraint. I just mean observations. So let's say I have a model here, p of xn comma theta. Right, and I make some observations xn, and I'm interested in going from a prior p theta to q theta. Right, so to a posterior q of theta. And one way of, well, if I actually then make the observation x1, the first observation is 5, I can immediately write down a posterior for I could say, well, q over x1 is theta, is delta x1 minus 5, right? That's a constraint on the marginal over, basically posterior over the observations. But I can also, I'm really interested in q over theta, and then the problem is, okay, how does this constraint on the observations, how does it relate to q over theta? Well, we can work it out by Bayes' rule. But there are other ways of adding information to the system. I can also say I'm only considering posteriors q over theta from the gamma distribution, right? Maybe that Bayes' rule would not actually automatically lead to a gamma distribution, but I can, I'm the engineer, say, no, I want it to be a gamma distribution. What is the best gamma distribution, the best parameters for a gamma distribution if I limit my posteriors to the gamma distribution, or other constraints, moment constraints. If I say, well, whatever q is going to be, I want the mean value of Q to be 3. And aside from that, any Q is fine. So as you can see, there are various ways to constrain the posterior, where adding data to the system, making observations about X, is only one way of adding constraints to the system. So this is a bit more general, right? Bayes' rule can deal with updating P theta to Q theta, the posterior, if my constraints come in the form of data. But Bayes' rule doesn't know how to go about it if I have other constraints. And the framework that we're going to talk about actually will accommodate that. So now I'm going to take the next step, and the next step is talking about the method of maximum relative entropy. And I want to go back first to what we said about probability theory. There are two ways to go about probability theory. You can just say, as a mathematician, here are the rules, these are the axioms, here's the product rule, here's the sum rule. And so now let's think about how to interpret that in the real world. Can we apply this to physics or to economics, and how should I interpret these probabilities then? Are those frequencies or what are they? Or, and that's what we did in this class, you can actually start with the meaning, right? You can start with saying, I want to have a calculus for dealing with uncertainty. I want to represent beliefs over propositions. And I want, whatever that calculus is, I want to have certain properties that I need to adhere to. For instance, if I believe more in A than in B, and I believe more in B than in C, then I must believe more in A than in C. And if you impose a couple of those constraints, then you can derive that probability theory is really the only calculus that's left over. And so now there is no more uncertainty about what is the interpretation of probability theory. You started with an interpretation. You want to have a calculus about uncertainty. And by imposing a few rules that are very agreeable, you wind up with the product and sum rule. Here we're going to do the same thing. We're going to say, now suppose I have some prior P of Z about variables Z, and I get new information in the form of constraints. So this could be data constraints, but also could be form constraints on Q of Z. Or moment constraints or other constraints, right? But I have new information in the form of constraints. Now, what is the best posterior, what is the proper posterior for Q of Z? And so what people have done, and there are references in the notebook, is they've said, okay, let's come up with a ranking function for Q of Z's, for candidate posteriors. And that ranking function is this function here. This is a function S. The function is called the relative entropy. It's a function of both the posterior Q and the prior. And the idea is, or the statement is now that when information is supplied in the form of constraints on the posterior, so constraints on Q of Z, we have to select a posterior that maximizes this function subject to the constraints. This function is called the relative entropy. And this is derived, this theorem is derived again from some very agreeable assumptions. So we didn't start out here by going to information theory and looking up what is entropy and maybe it applies to our problem. But we do it the other way around. We say we have here a problem of I want to come up with a calculus or a method for updating a prior to a posterior. And whatever that method is, the method is going to be, I'm going to have a ranking function for candidate posteriors. And whatever that ranking function looks like, it must agree to some very very trivial assumptions that you almost cannot disagree with. If you make those assumptions, then this has to be the ranking function. So that's important. Again, so it's a similar kind of derivation. We started with the meaning and we arrived at the ranking function. So you may think now, okay, so is this an alternative to Bayes' rule? No, as we will see later, this is completely consistent with Bayes' rule. Bayes' rule is just a special case of this method. So that's the theorem, or the method, maximizing relative entropy. Now, there's lots of scientific communities that use this this function, and they give all different names. The name that we are going to use, or the form that we're going to use, is going to be called free energy. And I'm going to show you the relation. Basically, the first relation is, I want to introduce the Kullback-Leibler divergence. The Kullback-Leibler divergence is nothing but just the negative relative free energy. So if I take away this minus sign, then I end up with, well, the Kullback-Leibler divergence of Q of P, and the minus is gone. So it's this function, and so it's a negative relative entropy. And I can also say now, if I go from a prior P of Z and I have new information in the form of constraints, and I want to go to Q of Z, a posterior, I must minimize this function subject to the constraints. Now you can prove, and the proof is just a few lines. If you press here, you'll see the proof on Wikipedia, that this function is always greater or equal to 0, this Kullback-Leibler divergence. It's only 0 if P equals to Q, and in any other case, it's greater than 0. So only when Q and P, when the posterior equals the prior, then the KL divergence equals 0. We're going to use in our class a little bit of a generalization of the Kullback-Leibler divergence. Namely, we're going to say, well, I'm going to allow P, my prior, to be unnormalized, right? So I'm going to say I have P of Z, and P of Z is some positive function f of Z divided by, well, Z, and that is the normalizer. And now I'm going to write down f, my free energy function, in the same way as the Kullback-Leibler distribution. You can work this out, and it turns out this is just the Kullback-Leibler divergence minus log Z, but Z is a constant, so just a shift in the Kullback-Leibler divergence. So minimizing free energy, again, is the same as minimizing the Kullback-Leibler divergence. So that's the function we're going to be working with. Why is it called free energy? Well, there's a relation to thermodynamics, to physics, where we call it Gibbs free energy. This is a concept that actually was started by Feynman, the famous physicist. The nomenclature has a physical slant to it. Okay. So let's go ahead now. Let's go ahead. So I have here a model P of X and Z, where X is observed and Z is unobserved variables. They could include parameters, hidden states, latent variables, anything you want. It could be a whole set of unobserved variables. And I assume now that X is observed as X hat, and we're interested in performing inference. So what does that mean? We want to compute the posterior P of Z given my observation for the latent variables, and also the counterpart. I want to compute the evidence, right? Basically, Bayes' rule rewrites prior and likelihood, or the generative model, into a evidence term and to a posterior. Now the principle or the method of maximum relative entropy says what you want to do is you want to minimize this function here. This is the free energy functional, right, with respect to Q. And I've written it out here. This is the generative model. This is the posterior, right? So this is sort of the this is the prior now. This is the posterior. And what are my constraints? Well, I have a data constraint. X happens to is observed at X hat. So let's work this out. The data constraint fixes the the posterior for X, the marginal posterior for X on delta X minus X hat. And I'm going to plug that in here. So I'm going to get a sum over X and Z. This is the joint over X, joint posterior. This is the joint posterior. This is the joint generative model. I'm going to plug in here in QX here. I'm going to plug in here the delta. That is my constraint. Well, then my sum over X, I can really write that out by plugging in the observed value here, plugging in the observed value, and plugging in the observed value here. And I can split this factor here out of here. And this is now my free energy functional. I need to minimize this with respect to Q. Since, I mean, here I used to say F is a function of P and Q above. Of course, it's a function of P and Q. But if I'm only interested in minimizing it with respect to Q, so then we write it just as F of Q. Also note the square brackets. The relative entropy and the Kullback-Leibler divergence and the free energy functional are functionals, meaning they are functions of functions. F is a function of Q, but Q is a probability distribution, is a function of Z and X. So that's called a functional, and the calculus of functionals is called variational calculus, and that's where the term variational Bayes and variational inference comes from. But crucially, F of Q is this guy here at the bottom. It's quite easy to derive that, and we need to minimize this. Now note that this here is just a KL divergence. It's the sum of Q over Z and P over Z and the expectation. So this is a QL divergence. So this is always greater equals 0, except that is only 0 when Q equals P. This is not a function of Q. So it's very easy then to see how F is minimized. F is minimal with respect to Q if here the numerator QZ given X hat equals PC given X hat. Well, that's the Bayesian solution, right? So I get my global minimum if Q star, global minimum, if Q star equals, well, the Bayesian posterior. At the same time, then this term goes to 0, and all I'm left over with is basically minus log P of X hat. Well, P of X hat is the evidence, the Bayesian evidence, right? So the minimal free energy, which I get by plugging in my optimal value for Q, is just basically minus log Bayesian evidence. Or in other words, the Bayesian evidence is the exponent of minus the free energy, where I plug in my optimal solution, the minimizer. In other words, by minimizing the free energy, I can do everything that I need to do for Bayesian inference. I get my posterior, the Bayesian posterior, and I get the evidence, right? That's crucial, and this is quite amazing, because I had a Bayesian inference problem, and executing Bayes rule requires integrations. We need to, in order to compute the evidence, I need to integrate out over all hidden variables. So the problem in Bayesian inference are usually those integrals. And now we've translated it to an optimization problem, a minimization problem. Usually minimization of functions or functionals is a bit easier than integration. So that's a good move. So Bayesian inference, computation of the posterior and the evidence, in case there are only data constraints, can be executed by free energy minimization. And that is an amazing result, right? Because we go from basically from integration to optimization. Now, in general, as I said, f is a function of q and q is a function of variables. I may have hundreds of hidden variables. I may have lots of observed values. This could be a very difficult function to minimize. So we may not get to the global minimum. We may only be able to find the local minimum. Note also that f is a function, changes if my observation changes. So if I am in a dynamic situation and I get observations over time, then my function, my free energy function changes. So I have a moving target if I want to minimize, right? My objective function changes over time because the observation changed. So minimization is not straightforward. But still, what people do is we just try to minimize it the best we can. If we don't get to the minimum, then we can still call it approximate Bayesian inference. We might get a local optimum, and we can use that as a proxy for your Bayesian posterior, and the free energy, where I plug in my local minimum, is going to be a proxy for the evidence. In a sense, what you do when you do free energy minimization, there is only one goal. You pick a model and you minimize free energy, and then you can pick another model and you minimize free energy, and the model with lowest free energy wins. That's the one that has the lowest evidence, right? So that's how that works. Now, executing this minimization may be difficult, and that's when it's very handy to add additional constraints on Q. So then we talk about constrained free energy minimization, right? And there are three really important classes. One class is, we can say, well, aside from data constraints, I make observations, but my posterior over my hidden variables, I'm going to say that they're all independent from each other, right? So the posterior over Z1 is independent of the posterior of Z2 and independent of the posterior over Z3 and so forth. This may not roll out of Bayes rule if you would just implement Bayes rule. It's something you impose to make the computation easier. That also means you are now in the business again of approximate Bayesian inference. But if it actually turns out that by making this assumption you can do the computation, you can actually minimize the free energy, then it may be worth it. And in practice, this is a really valuable assumption. The other way, of course, is you say my posterior over Z is going to be parameterized by a Gaussian or by a gamma or by a beta distribution, and I only now need to find I need to optimize these parameters mu and theta. If I do that, then my function of f of q now reduces to a function of the parameters of q. So now I have a regular function of parameters, and I can just try to minimize that function by some optimization library. Right. The third form is to basically cast maximum likelihood estimation as a free energy minimization problem. That is called expectation maximization. Expectation maximization is a very popular algorithm. It's slowly becoming less popular because of the probabilistic programming languages, which allow us to do Bayesian inference, and maximum likelihood is a very severe restriction on Bayesian inference. So I'm just going to push this now, this expectation maximization algorithm, to the optional slides. We had to make some choices in what to treat and what not to treat. But you may actually encounter expectation maximization in papers in machine learning, and then it's maybe good to read the optional slides, because what is interesting is that the expectation maximization algorithm can be cast as a free energy minimization algorithm with some constraints. So what we're going to do is, just as an example, let's implement now this constraint. So on top of data constraints, I'm going to assume this mean, as they call mean field constraints, high factorization in the posterior. If you do that, if you assume that, then you can, and this is worked out in Bishop, and this the Bishop's equation 10.9, you can work out the solutions actually. So the optimal posteriors for these marginals over Cj, they are a function of, basically I take the whole generative model or the log thereof, and I take the expectation with respect to all z's except for j. Now x is observed, and z is maybe a very long vector, and I integrate out the expectation over all g's except for j. So this now becomes a function of zj, and that's called the mean field. Why? Well, it relates to physics, but this you can interpret it as a field in physics, and basically you take the mean of that. You can work this out. There's a proof actually of this. And you can work this out now, this equation for the Gaussian distribution. There's one more thing I need to say about this. The solution, so the posterior solution for z of j is a function of basically the posterior solution for all other variables, and I mean actually the solutions. And the solutions for the other variables are, again, by the same formula, a function of z of j. So there's sort of a chicken and egg problem. And what we have to do is we just have to iterate through this. Update for one variable, for another, and for another, and for another, and go around. And that works well. You can then, actually when you do that, that leads to an algorithm called coordinate ascent variational inference. You can look in this paper, and if you look in that paper, you will actually see this. So there's a model, there's a data set. Basically until convergence, you set q of j, cj to that formula. And then when you do that until convergence, you return q of z. That's the workhorse of mean field variational inference. And it's a very good approach. For instance, we can do this now for our Gaussian mixture model. We go back to the illustrative example in the beginning. I'm going to have, so this model assumption, this is the Gaussian mixture model. I'm going to set some priors. Right, so I need to set some priors on the parameters, on pi and on mu and on lambda, and then I have my full generative model, and I can now I'm going to do inference, and I'm going to aside from data, I'm going to impose another constraint. I'm going to impose a factorization constraint. I'm going to say q over all hidden variables is going to be split into q over z, my class labels, my cluster labels, and that's going to be, that posterior is going to be independent of q over the parameters. In order to come to a solution, it's not necessary to make further factorization assumptions. You can, but it's not necessary, because if you just make this assumption then you can come to analytical answers, right? And in Bishop then shows the analytical answers. They are written out here. Of course, I don't expect you to really derive these things in class. Just show it, and I hope you understand really the line of reasoning and what has to be computed. But to actually work this out to these equations, that's worth a paper, or at least it was when it was first derived. It was worth a full paper, a scientific paper, and so it's a bit too difficult to do this just let's say in an exam. But it's still good to see that. And then, well, we implemented that. So we do free energy minimization for the Gaussian on that old faithful data set with mean field assumptions. And so here's the code. And when you run that, you get basically this. So here the data now is all in red, but there is no class label. We start with 6 classes. We don't know, right? So let's just start with 6 classes, random assignment of parameters. And so here are these 6 classes. Here's 2, 3, 4, 5, 6. And then this free energy minimization, due to the factorization in QZ and Q of the parameters, basically we update QZ and then we update the parameters and then we update QZ. And the way it goes is, once I have class labels, I can actually update the parameters, because now, or at least once I have Q of Z, an assignment, if you will, or an expectation for my class labels, I can update the parameters given my knowledge about the class label. And once I have class labels, I can, once I have parameters, I can update my class labels again, and back and forth. And so after 4 iterations, it looks like this. So these 6 classes are also kind of grouped into, they basically go to where the data is, and the dots here are labeled with Q of Z. So you see here they become more green, go to the green class. And this one is sort of pink, it's undecided almost, right? And after 6 iterations, the posterior Q of Z over the class labels becomes even more clear. You can keep going. In the end, you will just end up with 2 classes. 4 of the clusters will just disappear. You get 2 clusters, and for also a good posterior for basically for each observation, it's going to be very clear it belongs to this class or to the other class. So this whole problem now, we have learned the mean, the variance, the priors. We've also learned the class labels, the cluster labels, and we've learned basically the number of classes. So, and everything is just free energy minimization. So it's a very powerful technique. Basically this is where the most modern research on machine learning is about exploring what we can do with free energy minimization or variational inference to much more complex problems with lots of hidden variables. So this is also, this variational inference is what is behind when you do probabilistic programming. And since we're at the university, I think we need to know what goes on behind the scenes, and so we don't just use the toolbox, but we actually want to know how it works. So that's a variational inference, a very powerful generalization of Bayes' rule, where we can impose, or we can import not only new information in the form of data, but we can also impose constraints on Q, on the posterior, and that makes the problem doable. You get approximate Bayesian inference, but much rather do approximate Bayesian inference than no Bayesian inference at all. So this framework allows to do that. In Bayes' rule, you can really only process new data. This is more general. It's based on very fundamental reasons. It's very sound theory, and it's a very potent method. And lots of algorithms that are very, let's say, that in the past have been derived and work very well, like expectation maximization, turn out to be special cases of free energy minimization. So that's this class. There is a lot more in the lecture notes, so please read the lecture notes, and yeah, write down your questions or come with your questions to class, and then we'll talk about it. Bye.